In an earlier lecture, while mentioning the various functions that an air conditioning system performs, I had also identified the noise levels as one of those parameters that should be controlled in a system, and in this lecture that is what we are going to look at. So the first thing that we will look at is how do we quantify sound, what is noise, and then we will move forward. So when we want to identify define sound, so what it is, it's actually a variation in the pressure above the atmospheric pressure that is sensed by the human ear. That is, when those pressure waves that are produced strike the eardrum, the variation in that pressure above and below the atmospheric pressure is sensed by the eardrum and we perceive it as sound. The sound pressure is measured in pascals, and another important parameter that we work with is the intensity of the sound. Not just how much energy there is, but what is the rate at which that energy is transported past a given area per unit time. So that will have units of watts per meter square, and that is the sound intensity. If we look at the typical ranges of sound intensities, the human ear can detect a intensity level as low as 10 raised to the power minus 12 watts per meter square, and then we can go upwards at some point. If the intensity becomes too large for a human, that will become uncomfortable, and ultimately it can lead to damage to the eardrum as well. And the measure of the intensity of sound is generally referred to by using the units of decibels. So the decibel scales is a logarithmic scale, and it is defined as 10 into log 10 of the ratio of the intensity of the sound that you are measuring divided by the intensity of a reference sound, and that reference sound is the threshold of human hearing, that is 10 raised to the power minus 12 watts per meter square. That is, if we look at the equation by which we can evaluate the decibel level of a particular sound, I will be the intensity of that particular sound, and we will divide by I reference, which will be equal to 10 raised to the power minus 12. And just to give you an idea of the intensities of various different types of sounds, we have got a table which starts with the lowest intensity that we can detect, so that will be converted into a decibel level of 0. Then as you move to higher intensities, we have typical situations for which the intensity levels are given, and if we have an intensity of 10 watts per meter square, that will be equal to a decibel level of 130, and that is when that sound will actually cause you pain. And at an intensity level of 160, there will be a permanent damage to the eardrum, and that is what we must also keep into account when we design an air conditioning system. That is, what is the noise level. You will see that there is going to be another parameter that we will work with when we talk about HVAC equipment, but the starting point is this intensity level by using the decibel scale. Now the question is, when does sound become noise? Because sound will always be there, and at times that is required, but sound will become noise when it has certain adverse effects on the person who is in the conditioned environment. For example, when it is too loud, or it is an unexpected sound, a sudden sound that is disturbing, or you cannot control it, it happens at the wrong time, or it can contains unwanted tones. For example, if you have a fan and the bearing wears out, then as the fan is running, there will be an additional sound due to that worn out bearing, and that will cause you that will distract you from whatever you are doing. And you can also have other distracting sounds which are then classified as noise. It can also be an unpleasant sort of a sound, for example a dripping tap, so you actually lock on to that particular sound, and then that also is discomforting. It can also be based on a psychological experience. For example, somebody who's been into a difficult situation, going to a hospital, so the sound of a siren also can cause actual discomfort to that person. Or you can have a combination of these various factors. What we will do now, we will go through a video in which you will be introduced to some additional knowledge regarding sound and noise, and then we will return back to the next related topic.
Welcome to Noise Control Fundamentals. In this module, we're going to explore the importance of understanding noise control and how it relates to air distribution. Noise control can be just as critical as environmental conditioning when it comes to air conditioning systems. Human comfort is greatly affected by the noise levels in the environment. Too much sound or unwanted sound can create unpleasant living conditions, but the absence of any sound can also create uncomfortable conditions for the occupant. The right mix of sound can cleverly mask unpleasant noises such as conversations, computer equipment, and office machinery. To obtain the proper level of sound in a room, the right ventilation system must be selected and tested to ensure the optimal level of comfort is achieved. In this section, we will learn exactly what sound is, how we measure sounds in our environment, and how to add sound sources. Once we understand the basics of sound, we'll then look at testing, the price testing facilities, and the importance of properly configuring a room with air distribution equipment in order to achieve the maximum level of comfort. What is sound? The range of hearing for the human ear is extremely broad. We can hear sounds as low as a blade of grass blowing in the wind to the roar of a jet engine as it takes off. Sound is an active part of our everyday lives. Sound can be pleasant and provide comfort and relaxation, or it can also be considered a nuisance or a disturbance. Sound is basically any pressure variation that the ear can detect. These pressure variations are caused by a vibrating object or surface, or by turbulent air or gas. Noise, on the other hand, is any annoying or unwanted sound. What differentiates a noise from a sound is subjective, but is often due to its volume or tonal qualities. If we can determine what differentiates sound from noise, we can better address the issue of noise control. And to do this, it's important that we understand how to measure sound. Measuring sound. A pressure variation in a sound wave can be measured in micropascals to determine its loudness. The greater the pressure variation there is in a sound wave, the louder it'll be. The micropascal is an actual physical measurement of the pressure variation in a sound wave. The weakest sound detectable by the human ear is 20 micropascals. To put this into perspective, a pressure change at this level causes the eardrum to displace less than the diameter of a hydrogen molecule. At the same time, the ear can also withstand pressure changes more than 1,000,000 times this lower threshold. This type of measurement would result in a rather large and awkward scale. To avoid this, another scale is used, the decibel or dB scale. Compared to the micropascal, the decibel scale gives a much better representation of the way humans perceive relative loudness. This is because the ear does not react proportionately to changes in volume level, but does so according to a logarithmic scale. Note that while the micropascal scale is a literal, linear measurement of sound pressure, the decibel scale is more compressed and focuses specifically on the human range of hearing. Please experiment with the following interactive screen to better understand sound levels. There are some important things to remember about decibel measurements. A change of 3 decibels is barely noticeable. This is the point at which the human ear recognizes a change in volume. A change of 5 decibels is a clearly noticeable change. A change of 10 decibels appears to be twice as loud as the original sound. Frequency. Frequency, which is measured in hertz, is the number of pressure variations that occur per second in a sound wave. The sound's frequency produces a distinctive tone. This is why a flute, which has a high frequency, and a bass drum, which has a low frequency, sound so different. The range of human hearing is anywhere from 20 hertz all the way up to 20 kilohertz. The human ear is most sensitive to sounds between 2 kilohertz and 5 kilohertz. Please experiment with this interactive screen to better understand frequencies. Adding sounds. Because the decibel scale is logarithmic, the addition of sound levels cannot be done directly. Let's take a look at the concept of adding sounds. The following formula can be used when combining sounds. Press the Solve button to see the solution. Alternatively, the following chart can also be used to determine sound totals in decibels. At the bottom of the chart is the difference between the 2 sound levels to be added. The numbers found on the left side of the chart represent the decibel level to be added to the louder sound source to arrive at a decibel total. To better illustrate adding sound levels using this chart, let's take a look at a couple of examples. Take, for example, this mixer, measured at 65 decibels, added to the blender measured at 70 decibels. The difference in the 2 sound levels is 5 decibels. We find that value at the bottom of the chart and extend a line from this value upward and across the chart. The resulting number, 1.2 decibels, is then added to the sound value of the loudest source for a total sound level of 71.2 decibels. In this example, both hand drills have sound levels of 75 decibels. The difference in the 2 sound levels is 0 decibels. We find that value at the bottom of the chart and extend a line from this value upward. The resulting 3 decibels is then added to the sound value of either source for a total sound level of 78 decibels. Take, for example, this radio, measured at 75 decibels. Added to the lawnmower measured at 85 decibels. The difference in the 2 sound levels is 10 decibels. We find that value at the bottom of the chart and extend a line from this value upward and across the chart. The resulting number, in this case 0.4 decibels, is then added to the sound value of the loudest source for a total sound level of 85.4 decibels. Here are some rules of thumb to remember when adding 2 sound sources measured in decibels. If the 2 sound sources are equal, the resulting total will be 3 decibels higher than either of the measured values. If one source is more than 10 decibels greater than the other, the quieter source's contribution can be considered imperceptible. Remember that when adding 2 sound sources measured in decibels, the total will never be greater than 3 decibels higher than the loudest source. As you may recall, a 3 decibel change in volume is barely noticeable to the human ear. Sound power versus sound pressure. It is important to understand the difference between sound power and sound pressure when considering the measurement of an object's sound energy. Sound power is the total sound energy of an object, independent of any environment. We typically determine an object's sound power in a room with no dampening influences. Wherever possible, sound power levels are given for Hvac products to enable reliable side-by-side comparisons. Sound pressure is a measure of an object's sound level in an environment where dampening influences are an issue, such as wall hangings, carpeting, and furniture. Although catalog data provides a basis for product comparisons, the environment into which an Hvac system is installed can greatly affect noise levels perceived by its inhabitants. In order to understand the difference between sound power and sound pressure, let's take a look at three similar scenarios. Consider the analogy of a heater's warming effect on a room. The heater's heat output or power is rated in either watts or BTUs. This power output will remain constant. We can measure temperature at any point in the room with a thermometer. The size of the room and how it's constructed and furnished will influence the heater's effectiveness, but it will not change the heater's power output. Well-insulated walls and well-designed windows will help maximize the heater's efficiency. Your location and distance from the heater will also influence the temperature that you record. In this instance, we place a light source in the room. The light's output is rated in either watts or lumens and remains constant. The illumination can be measured with a light meter. The size of the room, its construction and furnishings can greatly influence the light's effectiveness. Light-colored walls and furnishings will tend to reflect light back into the environment, while darker colors will tend to absorb the light. Your location and distance from the light source will also affect any readings you might make with a light meter. Finally, let's apply the same scenario to a sound source. The object being tested has a certain sound power level. This sound power level can be expressed in watts or decibels. Sound pressure can be measured with a VU meter. The sound pressure levels recorded are greatly affected by the room. Cement, glass, and tile surfaces will tend to reflect the sound back into the environment. Items such as furnishings, wall hangings, and floor coverings will tend to absorb sound. Your location and distance from the sound source will also influence the sound pressure measurement that you make with a VU meter. From what we've explored in the previous three analogies, we start to understand that the term power is always associated with the energy emitted by an object. Therefore, sound power is the total sound energy of an object, independent of any environment. Sound pressure is a measure of an object's sound level in an environment where dampening influences are an issue. Testing. The availability of reliable sound power and pressure data is important when it comes to comparing and choosing specific products suitable for an environment. A key element in the price test facility is the Reverberant sound room, constructed to meet ASHRAE and ISO test standards. It is used to measure sound levels produced by the various price manufactured products. These readings are made under carefully controlled circumstances so as to determine the amount of noise produced by the item in the absence of any dampening influences. Sound absorption in the room is minimized by the specially coated walls and concrete construction. Background noise checks and regular calibration ensure that testing is done in a consistent and precise manner. The resulting sound data is published in the Price Air Distribution Catalog in order to help you select the right products for the right environment. Please explore this interactive screen to see the various components of the Price Reverberant sound room. Frequency Analyzer. Utilizing Brielle & Kjaer's state-of-the-art dual-channel real-time frequency analyzers ensures the highest accuracy of sound measurement available. Pressure gauges. Airflow and pressure measurements are recorded in accordance with industry standards, utilizing precisely calibrated meters and gauges. The sound room door is acoustically lined and constructed of metal. We use two separate doors with gasket seals to ensure a sound-tight environment. Calibration. Frequency analysis equipment is calibrated using a known sound source. Air supply and test subject. Air is supplied at precisely controlled rates to the test item. The room is outfitted with relief silencers which allow air to escape the room but prevents any noise from re-entering. Walls are constructed from concrete with a plaster coating and covered with an epoxy paint. By using the hardest surface possible, we maximize the amount of sound reflection in the room. The room walls are also constructed to meet specific height, width, and length requirements. Microphones. 3 microphones are placed in precise locations in accordance with ARI testing procedures. The microphone configuration ensures a representative sampling of all frequencies and sound from every direction. As you may recall from our previous chapter on frequency, frequency is the number of pressure variations per second in a sound wave. Although it is important to get an idea of how loud a particular product is, it's also useful to know what frequencies it produces. Unlike a musical instrument, which produces a specific note, a device such as a terminal unit, fan, or diffuser will simultaneously produce a vast variety of frequencies. For instance, a fan might produce a lot of low-frequency noise due to its motor. High-frequency noise might be produced by airflow through dampers or diffusers. The normal range of concern for most air terminal devices is in the 90 to 5600 Hz range. To derive frequency-specific test data, electronic filters are used to isolate noise occurring in the following frequency ranges. Note that each of the frequency bands center on a frequency which is double that of its predecessor. A tone with a frequency that is twice that of another is said to be 1 octave higher. The frequency ranges that we analyze are therefore called octave bands. Because the contributions found in octave 1 and octave 8 are often imperceptible in Hvac applications, we discard the data found in these frequency ranges before publishing results in the catalog. Once the original sound has been separated into frequency bands, we can then measure the loudness of each one independently. Please experiment with this tool to hear the kinds of frequencies that we analyze in our testing facility. NC levels. An NC value is the result of reducing all of the sound power data for a specific product into a single number. To accomplish this, we first estimate the sound pressure that an occupant will experience in an environment. Given that we can't predict how the product is going to be used, ARI has determined a conversion process that assumes that the device is installed in a typical room. Attenuation values provided by ARI are subtracted from the sound power levels determined during the frequency testing. This conversion accounts for various environmental effects that will attenuate or dampen the sound. Let's set these values aside for just one moment. If we take the adjusted figures from our octave band tests and plot them on the graph, we can determine an NC rating for the device. The lowest NC curve under which all of the test data fits is considered to be the device's NC rating. An NC rating is a single number that represents the perceived sound level of a device and is commonly used to rate noise levels of air distribution products. The catalog and selection. How do we determine whether a product is acoustically suitable for a specific environment? Sound power data and NC ratings for most products are readily available in the price catalog. Let's take a look at how this information is presented and how we can use it to select products for a particular environment. As you may recall, we placed the device to be tested into the Reverberant sound room. Sound data is presented differently in the catalog for GRDs and terminal units, So for this example, we will examine the discharge sound from a terminal unit. Most devices are tested by passing air through the device at various predetermined rates and pressures. The sound produced is picked up by the microphones and fed into the Brüel and Kjaer real-time frequency analyzer to be split up into octave bands. We determine the sound power produced by the terminal unit in each of the octave bands and publish the information in a format similar to that shown. We determine sound power ratings under a variety of airflow and pressure conditions. Note that as we increase airflow through the terminal unit, the sound power levels increase. Likewise, the tests for static pressure drops show that as air pressure increases, sound power levels also increase. Various sizes of a product are given as well. Typically, a larger version of a particular product will be able to handle larger volumes of air without causing a significant increase in noise. Here we show a typical sound power table for terminal units that might be found in the price catalog. For any given octave band sound power test, we can estimate sound pressure levels using this ARI conversion table. It assumes that equipment is being installed into what ARI has determined to be a typical room. We use the air capacity of the device to determine which numbers to subtract from the octave band sound power values to arrive at an estimate of the unit's sound pressure levels under typical circumstances. If we take the adjusted figures and plot them on an NC graph, the lowest NC curve under which all of the test data fits is considered to be the terminal's NC rating. Because we have sound power readings for various airflows and pressures, we can produce NC ratings that correspond to each of these combinations as well. This is a portion of a typical chart found in the price catalog, which shows NC levels for a terminal unit under various conditions. Dashes are shown for circumstances where the NC level is less than 20, since the noise contribution would be so quiet as to be imperceptible in most settings. These figures appear in the catalog in typical selection guides for terminal units. Similar data appears as performance data for GRDs. Note that when it comes to HVAC products, a device with a given sound power level may be suitable for some environments but not others, depending on the reverberant characteristics of the room and the client's needs. How do we know which products are suitable for a particular environment? ASHRAE publishes guidelines that indicate what NC levels are allowable for specific applications. If we compare the NC levels given in these guidelines to the NC levels published in the catalog, we can find products that are suitable for most any room. Configuration. Now that we understand the fundamentals of sound, let's take a look at applying these principles to noise control in an air distribution environment. When designing an HVAC system, the designer must be aware that noise can be transmitted to the environment via multiple paths. In addition to the noise produced at the air outlet, noise produced by fans and dampers can be transmitted through the ductwork itself or radiated via the ceiling cavity. An improperly designed air distribution system can generate unnecessary turbulence and noise in the occupant's environment. Here are some of the more common mistakes that can contribute to a less than perfect sound environment. Scenario 1. Poor selection or undersizing. If a diffuser is too small for the volume of air flowing through it, it will create excessive turbulence and noise in the room. By correctly choosing the right size of diffuser, this problem can be avoided. Use your price catalog to refer to sizing data and NC levels. Scenario 2. Improper installation of flex duct. Another factor that can contribute to poor noise levels in a room is the improper alignment of diffusers to the supply ducts, especially when flexible duct has been used in close quarters. Skewing or crimping the flex duct by half a diameter can add up to 15 decibels to the manufacturer's noise rating. By placing the diffuser directly under the takeoff and straightening the flexible duct connector, noise levels can be minimized. Scenario 3. Straight branch length. In an ideal situation, the diffuser should be situated directly at the end of a significant length of ductwork. Should conditions not allow for this placement, an imbalance in the airflow may result. Excessive air velocity through parts of the diffuser may add up to 12 decibels of noise to the rated NC level of the diffuser. An equalizing grid may be inserted to rebalance airflow through the diffuser and decrease noise. A general rule for placing any transition such as elbows, T's, and adapters in ductwork is to give at least 3 duct diameters of distance between any transition and a diffuser. Scenario 4. Poor duct design. If a diffuser is located too close to the terminal unit, damper and fan noise will be transmitted to the environment via the ductwork. It is recommended that there should be at least 3 duct diameters of distance before your first diffuser is placed. A reasonable amount of line ductwork should be used to dampen noise. Scenario 5. Damper placement. Because dampers create turbulence and noise, it is important to position them as close to the branch or takeoff as possible. The further away the damper is located from the diffuser, the better. Scenario 6. Line diffuser plenums. Care must be taken when lining diffuser plenums. Excessive lining in a slot diffuser plenum can decrease volume, increase air velocity, and may actually introduce significant noise. Price manufactured plenums contain an optimal amount of lining so as to minimize the amount of noise produced. Acoustic mock-up room. In order to demonstrate and experience real-world scenarios, Price has constructed a test room specifically for conducting acoustic mock-up tests for terminal units. The room has been designed and finished in accordance with Acoustical Consultants Guidelines for simulating actual office acoustics. Mock-ups can be developed for each project's unique specifications, including terminal unit type, size, air volume, ceiling construction, etc. Acoustic mock-up tests are a very effective method of verifying room NC levels as opposed to relying on the theoretical calculations for terminal unit applications. Visitors can listen to the system in operation as well as be provided with sound measurements. Noise control is a very important factor when considering an HVAC configuration. We hope that you've enjoyed this overview of noise control fundamentals. Please refer to the engineering section of our Price catalog for more in-depth information into product-specific areas of noise control. Contact your...
In the video, you heard about the transmission of noise through various produced by various HVAC equipment into the conditioned space, and this is an area that has been extensively studied, and based on those studies, ASHRAE has identified certain principal paths through which the noise is transmitted in an HVAC system. And you can see that figure on your screen, in which we have shown those various paths which have been identified by letters from A to E, and these noise transmission paths are typical of any large air conditioning system. As you had learned in the from the video, that there is a particular parameter NC, or noise criterion, that is used to quantify the noise produced by various types of HVAC equipment, and typically noise NC values of 30 are considered to be quiet, and NC values above 50 are considered to be noisy. And if you look at the ASHRAE handbook, in the ASHRAE handbook they have given us a table of the sound sources, again typical of air conditioning system, and the various paths through which those sounds are transmitted into the conditioned space. So the sound source is identified, and against that sound source you are given a number which is its path number, and in the next table you can see those path numbers are given over here, and against those path numbers you are also given the recommended noise reduction methods. So for example, if you look at a compressor that is running in the plant room, it will have typical noise transmission pass 4, 5 and 6. And if you look at this table, 4 will be noise transmitted through equipment room walls and floors to adjacent rooms. 5 is the vibration transmitted through building structure, and 6 vibration transmission along pipes and ducts walls. So there will be 3 paths through which noise will be propagated when a compressor is running, and for each there are certain recommendations for reducing those noise levels. This particular aspect will be further made clear to you by looking at another video that I'm going to just now bring up.
So let's talk a little bit about HVAC equipment itself. Let's begin with HVAC equipment indoors. So there are many sources of HVAC noise indoors. The outdoor parts that can get indoor sound, for outdoor units, that sound can come from the supply fans, it could come from return and exhaust fans, it can come from compressor noise breaking into one of the other airborne paths. It can also come from compressor noise creating pulsating fluid, which is then passed into the building in the refrigerant lines. With indoor units, the noise can come from chillers, it can come from variable air volume boxes, it can come from your fan coils. Noise can be induced by air turbulence, and this is particularly a problem with high-speed flow and undersized ducts. Likewise, very sharp duct bends also generate a great deal of turbulence that can turn into noise. And if the turbulence is low enough in frequency or pulsation rate, then it can induce actual duct wall vibration or oil canning. And finally, there are many paths by which the structures can vibrate and then re-radiate the sound indoors. Let's talk about some of these paths indoors. So let's imagine that you have an HVAC system in a room indoors. It could be outside but still separated by a wall. It could be on the roof separated by the roof ceiling system. So this is, in essence, even though this looks like a specific example, it's very generic. You basically have the unit on one side of a wall and a person on the other side of the wall, a receiver. What are some of the paths? Well, the vibration from the unit can go through all of the structures that it has access to and then re-radiate into the room as structurable in noise. The most obvious path is noise coming through the ductwork and passing right out through the supply grills. But it can also come out of the return. The sound doesn't care whether it's going out the supply or the return. It will go both ways just as happily. And finally, then the third way is breakout noise. There's sound of relatively high pressure moving through these ducts, and it can actually pass through the walls of the ducts. So that even though a duct may be passing down a hallway and have no registers locally, the sound can pass through the duct walls and into a room and be perceived as noise. And finally, the structure itself will allow noise to pass through it, and that's a combination of airborne and structure-borne paths. And so in HVAC, we need to worry about all of these potential paths. And so if you have a report of something being noisy, you need to be careful to try to figure out, well, what are the potential paths that are involved. There are lots of different ways to describe sound in rooms, and there are several that are most common in HVAC work. Primarily, there's often a desire for a very simple one-number metric for sound or noise. And really, dBA, a sound level in dBA in a room, is a pretty good descriptor. It works relatively well in being correlated by its level to how annoyed people will be. If it's lower, people are less annoyed. If it's higher, people are more annoyed. but that doesn't really well describe the timbre or quality of the noise, its frequency spectrum content. And so we use noise criteria curves, and so you'll often hear about NC ratings. And these are curves that are based on how people hear sound in rooms. They relate the sound level and the frequency distribution. And we take the sound pressure level in octaves and we map it out on a chart against these curves, and we note wherever the spectrum touches the highest numbered curve, that's the NC level. Unfortunately, for various noise criteria, there are several different ones. There's noise criteria, balanced noise criteria, noise rating, room criteria Mark II. These have all shown up in various requirements for HVAC systems. The most common two are noise criteria, the NC curves, and the room criteria, which ASHRAE has recommended in the past. One important thing to note is that you cannot plan as an equipment manufacturer for a specific noise control rating. The only thing you have control over is the sound power and the shape of the spectrum from your equipment, because in the end the noise criteria depends on the room itself and the size of the room and the amount of acoustical absorption in the room. But what are some of the kinds of things that you can do to reduce indoor noise from HVAC systems? Well, number one is, if you have the opportunity, planning is your best friend. You must assume that there will be noise, and you have to plan mitigations in advance. You have to pay attention to the equipment location in your space planning. And you need to size your equipment for low noise as well as proper capacity. Once installed, a low noise unit will do you a lot more good than trying to retrofit a noisy unit. For rooftop systems, you would definitely want to avoid locating immediately above some sensitive space like an office or a doctor's examination room. You need to use vibration isolation. You need to make sure that the mass and the weight and the vibration are mounted over columns of the building, not in between them. And it's often good to add a big thick mass on which the unit sits. That mass will help. It doesn't really absorb the vibration so much as it blocks its path. In terms of mechanical equipment rooms, in other words, having all the large noise-making equipment inside the building, again, avoid locating those rooms near occupied spaces. Use large air spaces and cavity insulation in the walls, ceiling, and floor surrounding the equipment room. Make sure that your wall and floor ceiling assemblies have a lot of mass so that, again, they break that path. And decouple the floors and ceilings between a mechanical and equipment room and any sensitive occupied spaces. And pay a lot of attention to your ductwork. Be sure to use attenuators and silencers if they're necessary. Plan on using absorptive linings for at least a fair amount of the main duct path. And then if you have breakout noise issues because of thinner gauge ductwork, there are many products available that allow you to wrap the ductwork and absorb and block the sound. Let's move on finally and take a couple seconds to look at HVAC equipment outdoors. Again, looking at sources of sound. When you're concerned with the sound outdoors, you've got chillers and compressors, condenser fans, and then other fans related to your units if you've got an air handling system that's outdoors. Because some of those fans have exposure to the outdoors. Although, in general, very rough rule of thumb, for an air handling unit, the compressors and condenser fans in general would be louder than noise coming from fans handling indoor air. We worry about sound outdoors because of noise limits and regulations. These limits on noise generated by HVAC equipment, they can be defined by many different sources. They could be the client itself. It could be a national regulation, a state regulation, a county regulation, a city ordinance. It could be some other jurisdiction like a homeowners association. There are many different sources, and unfortunately they have all different kinds of ways of describing the limits. In general, the most common limits outdoors are based on some maximum permissible sound level with a weighting. So it's a dBA rating. And it's most frequently assigned as being measured at the equipment owner's property line. So you can think of it as how much of my noise am I handing over my property line to the neighbor. Additional specifications, especially for city ordinances, might be to have separate limits for day and night, or day-night combined limits, sound levels in octave band frequencies over some range instead of just a single dBA rating. And sometimes they use, instead of a fixed level, they'll give a maximum exceedance above the existing ambient sound level or relative level. These types of ordinances are very difficult because defining what the relative level is can be a very big challenge, and there's often a tremendous amount of disagreement, even amongst competing experts, over what the existing ambient level is in a given area. How do you go about controlling the outdoor noise from your units? Well, in general, you have the same two choices as you have anywhere in noise control. You can reduce the source of the noise by selecting equipment that inherently makes lower noise, or by adding treatments on the fans and compressors of the equipment itself. Or you can alter the path of the sound. You can change the equipment's location. You can make use of distance. Remember, sound decays with distance. Most commonly, what you'll see people do is install noise barriers of some sort around the unit. That can be very effective, but it has to be planned out properly. It has to be executed just right, and it's not always as effective per dollar spent as you might hope. What can you do at the source? Well, always remember one of the most important rules of HVAC noise: slower is lower. If you can slow things down in the system, they will in general make less noise. So let's say you can add a VFD control to lower your condenser fan speeds, so that if you're not demanding absolutely maximum full cooling capacity at any other time, you're not demanding capacity, everything can slow down and thus quiet down. And in general, higher capacity systems can be spec'd and run at slightly lower speeds. You can look into low noise options from your manufacturers, such as quieter condenser fans or low noise compressors. And typically they come at a premium. There is often a price associated with that. You can put baffles and attenuators over your condenser fans. That's very common on very large fans. It's less common on smaller fans. But here you see a case where there are neighbors looking over the units. And so the noise that normally would never be a problem on a rooftop is suddenly coming right in their windows, and an attenuator is necessary. Or compressor blankets and enclosures. They're very popular as an attack on compressor noise. However, it's very difficult to do it right, and quite often these compressor blankets do not work as advertised, not because of poor advertisement, but because they have to fit absolutely perfectly with no gaps in order to be effective. Because again, sound gets through gaps. It's very valuable to be able to interrupt the path of sound outdoors. Remember, distance is your friend. If you're putting in something like a large rooftop unit, orient the condenser end away from sensitive receivers. Use the physical structure to block that sound. Avoid using line of sight to sensitive receivers. Use what's available to you. Mount your units so that they'll be blocked by the roof from line of sight, instead of locating them toward the edge of the roof where the receivers on that side will have line of sight and get more noise. If necessary, install barriers, but remember, they need to be high enough, they can't have gaps, and adding absorption or getting sound absorbing barrier panels can be a lot more effective. Finally, because it's HVAC equipment, you always need to be concerned about letting it breathe. So you may have to invest extra dollars in getting air breathing absorptive louvers to allow air to flow into the barriered space, but still have sound attenuation.
So this was a brief introduction to noise and noise control related to HVAC systems, and you can gauge by this short introduction that it is quite an extensive area which has been studied and worked upon extensively with lots of technical details, and additionally there are other issues which may be legal, and those are also to be taken into account when you plan setting up a HVAC system. We will conclude this lecture, and then in the next lecture we will take up a new topic.